We are doing our homework today, returning to the exercises that we didn't do last time, or I am. And then we're going to do some more new learning. I was a bit lazy last time, and I didn't get through a lot of these, so see what I can remember. I'm going to try and use code a little bit more as well. My spot in the software engineering category, but we'll see. All right, how's the stream setting up? How are we doing? Excellent. Good. Okay. Write out row 11 of Pascal's triangle. So we're going to try and do this with code just to make this a little bit easier to work with. So I'm a bit less bored doing it. But I also got my... More indeed. How are you doing? P signal. Okay, so I think for question 1, which is where we're at, it's somewhere in this chapter. It says, I'm just going to have to erase that now immediately. Somewhere in this chapter it says how to do this using choosing, which I think it says it's 8 choose K for this, I think. Gives us the row of the triangle, so I'm going to try and do that. I will say for anyone watching back on the recording who's about to endure some terrible Vim usage, there you go. I apologize. Okay, so in theory, turn that off. In theory, we've got, let me just check this. So we would have 8 choose, or do we even have choose in here? Let me just check that. We do not. I think there's something. There's something somewhere. Comb. 8 choose 1, 2. Okay, so we start with 0, 1, 2, 3. Okay, good. And we're going to say our row is going to be this, and we've got 4 space indentation on still. I suppose I can handle that. Make sure I don't get my off by ones off by 1. Okay, we get 0 through 7. We might want more than that. Hello, Bobladon. Yeah, Blaise Pascal. That is Blaise, right? That's how you pronounce that. Yeah, he's got a great triangle, one of the great triangles. Every thinker loves to produce a triangle, by the way. I hope to name a triangle after myself one day, but not there yet. One of the triangles of all time, that's true. How are you doing, Bobladon? How's life today? Now, can I remember anything about writing code at all? Okay, we want +1, I guess. Okay. Then we've got that, and we probably want to have it. Actually, I don't think we need to have it organized as a triangle. I think that's just very wistful. You attended a seminar where one of your student friends presented his thesis. Cool. Was it a good thesis? Kind of want to wash my hair before friend dinner tonight, but also want to watch. Well, it's an impossible decision. We have something in common, Bob, which is I also wanted to wash my hair today before streaming, but I didn't because I was very disciplined. I was told as a young person, I was, my parents managed to instill only a few moral virtues in me, and not washing your hair every day is one of them. They didn't manage. That's basically the only one. That's the only moral framework I have. As long as you don't wash your hair every day, it's fine. And I kind of wanted to wash my hair today. Sometimes I indulge myself and I let myself wash my hair every day, but it's a rare occasion these days where I'm allowed to do it. Yeah, that gym person hasn't been calling me, I don't think. Sadly. He was, I think, in his, well, I don't think I was his type, but he did do an incredibly poor leg press. He did some incredibly poor leg presses as well, so he wasn't my type either. It was like, that the guy who's going to live forever, his leg press that everyone made fun of. It was, I guess it's okay. They were considerably worse than that. Thank you, Bob the Don. Or as we would say, fringe. My fringe is looking fringing. So we say that in the UK. Okay, we got 8. We got number 8. We also got some new noise today. I really mulled over what noise I wanted, and we've got crickets. I believe at some point a dog may bark, so watch out for that. I thought about putting on an English village because I like the birds sound familiar to me, but there was a bit too many church bells in it. Okay, 11. That looks about right. About time. I've been hearing something in the universe wants me to watch that movie at the moment, but I haven't seen it yet. It's no spoilers, obviously, but they say there's a guy. I can't spoil it because I don't know what happens, so don't take any of this as truth. In about time, here's my guess. In about time, there is a man and there is a woman, and the man, this is from the synopsis I remember, the man can travel through time, and his family has always been able to travel through time. Probably they're going to do something with that. He's going to maybe meet his family or something. But there's a woman, and he does some stuff. Rachel McAdams. Rachel McAdams must be the woman, probably. I'm going to get sunned on too much as well. That's the danger here. Okay. So I'm going to say this is row 11. Let's say that's row 11. Use the binomial theorem to find out. See, I did this before. I did this last time, I think. But I'm just going to work it through again. Use the binomial theorem to find out the coefficient of 8x8, x to the power 8, y to the power 5 in x plus y 13. So I've got a blue dot on my face. Terrible. Let that go away. Yeah, so this is the whole This is this thing. We get a coefficient. It's going to be in row 13. Yeah, it's going to be in row 13. And we're going to be looking at... Yeah, I definitely did do some of this. It's coming back vaguely now. Yeah, so the way it's supposed to work is if we had like row... If we had row 13, then we'd have like the coefficient for... What is it? Yeah, the coefficient for x13 y0 here, and that would be the first cell. Then we have x12 y. Then we have x11 y squared. Yeah, and then we go through x10, x9, and x8. Terrible 8 there. Let's get rid of that. So it's going to be, yeah, and then if we... Sorry, I'm just, everything's all over the screen today. I need to sort my window management. Let me sort this out as well. Okay, so we're looking at row 13. And we've got... So this one will be 1. This will be... Get rid of that, get rid of that, get rid of this. Put this in a different colour. This one will be 13. This one will be 78. This might not even be the right question, but I feel like I'm teaching myself something anyway. This one will be 286. This one will be 715. And this one here will be 1287. Okay, and then, you know, we could go along as well, and of course we'd have all the other y's in here, etc. Now, does this get us any closer to an answer? What's the question again? Use the binomial theorem to find the coefficient of x8, y5 in x plus y13. So the coefficient would be this. This here. Now I've got a new drawing system up, so I need a place to put my answers. And I think I'm going to put them up. I'm going to put them up. I'll put them up here. So I've got 1. I've already worked out 1. Terrible. Be neater. Be neater. There we go. Let's say 1, and 1 is going to be the 11th row. So let me write this out. Gee. You know, this would be a lot better if I didn't have all of these horrendous things here. I love these car noises as well. Okay, 1, 11, 55, 1, 6, 5, 1, 330, 4, 6, 2, 4, and then it's just reversed. So, etc., etc., etc. Now for 2, we're going to have the answer be 1287. Okay, and then 3 will come 2. Okay. Hello, George. It is Vim. It's NVim. Bobbledon says, remember you also had a few exercises from the previous section that you're a bit too tired for end of stream. Was that? I thought this was I thought this was that part I was doing the last section of. Maybe maybe I do need to go back. Okay, thank you for the reminder. Oh no, it is this section, yeah. And then there's another one. No more ed. Well, there'll be some ed at some point, but there's no ed today. And I'll try and use NVim in an eddy way. But yeah, that's true. I could crop, but then I'd lose the left-hand side of the anyway. I'll configure whatever. I'll do whatever horrendous configuration I need to do to get the tildes to go away at some point. But yeah. Until then, I could actually do something else. Yeah, but don't come here if you love to see Vim used in a really very proficient way, because I'm very new to Vim. I'm less than a month old as a Vimmer, so you're likely to see a lot of terrible. I still, thing is, I still even use that arrow buttons. I still even use the mouse. Terrible. The red dot. You want to know what the red dot does? The red dot moves around. It moves around independently. Look, they can kiss. You know how much time this took just to get this working? Ridiculous. They can dance. They can have a little party. Yeah, the blue, that's pencil, Apple Pencil. The red currently does nothing. Not quite sure how I'm going to get the 2 cursors. Why even have 2 cursors? I just decided 1 cursor. That's a bit of an architectural decision I'm not sure about yet. Why bother? Just have 2. But I don't know why. but it's kind of a, yeah, anyway. But I kind of want to treat the cursor and the pencil separately because they are separate. I want to use them differently. So, but I got the pencil, so I don't have to like write with the mouse now, which is pretty good. And yeah, one of the fun things about the latency was a nightmare. So I had to buy my iPad is currently connected to my laptop via Ethernet. Why do these things? Why? Just unnecessary. Anyway, what was I doing? Oh yeah, use the binomial theorem to find the coefficient of x8 x to the power 8 in x plus 2. So this one's going to be different, right? It's still 13, so we get these coefficients, but we're also going to have to multiply by 2 because we're also going to have a, no, actually, it's not going to be 2. It's going to be, so this is going to actually be x8, y something. So here it's y0, y1, y2, y3, y4, y5. Now this is actually going to be 2 to the 5, which is going to be, should know this, 32. I really need to memorize that. What kind of an influencer do I call myself? I can't memorize the powers of 2. 32. So that, apologies for the mouth noises, that is 32. So the answer is going to be 32 times 1, 2, 8, 7. Now what is that going to be? (32) times 1287, that's 41184. Okay. So that's the answer, allegedly. 4, 1, ooh, 1, 1, 8, 4. Thank you, and Stucky. Happy new week to you. Happy old week. PySignal says, Douglas Engelbart type networked computing with multiple cursors, did he? Uh-huh. That's cool. What was he doing that for? He's the Mother of All Demos guy, right? I'm remembering that correctly, right? Yeah, I guess, yeah. I feel like I did watch part of that. To watch the other part. But I do remember there being a lot of weird stuff in that demo. Maybe I can believe it. What time is it where you are in Stucky? Good to see you too. Every user on the machine could use a cursor. Wow. He was really ahead of his time. That is cool. Yeah, it's funny now because it's quite normal actually, I guess, on a lot of systems to have multiple cursors if you have like a shared whiteboard or even a Google Doc. But an individual computer does not allow it most of the time. Just before 9 a.m. Cool. A good time. Good time to be up. Okay, where were we? And what window do I have highlighted? Okay. Now, let's get rid of that. Question 4. Use the binomial theorem to find the coefficient of x6, which will be further along, y3, and it's also a different number, so we can get rid of this. Now, we've got 9, but we've also got some other coefficients. And we've got a negative. So we're going to have a little bit of work to do. Okay, well first let me work out the 9s. And let me just note those down. So we've got, gee, I don't even need to note them down. I just need to note down the right one. Now, the right term is going to be x6. So we've got x9. There's got to be a way that I should be memorizing whatever the rule is, right? It's going to be the n minus something row. So n minus, so if n is like 9, then n minus 0 is going to give us the first term. It's a silly way of thinking about it. Basically, I want to have n minus something gets 0. And so this is going to be nine. And the relation to x is Oh, my facility with this stuff is not great. Yeah, and then for the next one, which is going to be 1, we want to have it be n minus 8. Yeah, so it's like, it's n minus n minus, so if the term has like the x power or something, so if the x power was 9, no, actually it is just x, it's just x, isn't it? Yeah, it's just n minus the power of x. So if the power of x was 9, which I think is where we start, then we get the 0th one. So actually, since it's x6, it should be well, 9 minus 6, right? Which is 3. Number 9, plan 9, 9. Or I can subtract the power of y. Well, that would be a lot better, wouldn't it? Yeah, of course. Yeah. Yeah, in fact, you know, if we look at this, you're totally right. That's really obvious to me now. This tells us the cell in the triangle we want to look at, right? The y term, because it starts off at 0 and then it's 1 and then it's, yeah, okay. Right. Well, that's a lot better. Yeah. Okay. In which case, let's write down, so we want the third one, which is 84. Should I do this up here? 84. And it's going to be 84 times 3x to the power 6 no. No, it is that. And then it's minus 2y to the power 3. So we then end up with like the coefficient's going to end up being 84 times, I think, times 3 to the power 6 times minus 2 to the power 3, I think. So we can probably just calculate that. .84 times, sorry, yeah, no, it is 3. 3 to the power 6 times minus 2 to the power, minus 2 to the power 3, I think. That's not right. Or is it right? Doesn't look right. I guess it could be right. Well, it's a third power, so it will end up being negative, right? So if my calculations are correct, which they might not be. This should be 4, 8, 9, 888. Okay. Good. We've got a fact check. Bobbledon's fact checked it, so it's probably right. 4, 8 minus 4, 8, 9, 888. Let's assume Python can calculate reasonably accurately. Okay, question 5. Use the binomial theorem to show... I've got a show. Yeah, see, this one I did before, I think. Yeah, I did this fifth one. Now, can I remember? Can I? It's not really much point. There's not really much use having done the exercise if you can't remember how to do it. So yeah, we don't need Vim anymore. Now for this one, yeah, we had some notion. Yeah, we had some notion. Yeah, so we're summing up here. We're summing up all the n choose k's from k to n, and that's going to be a whole... So this didn't occur to me last time, but that's going to be a whole row on the triangle, right? Which is kind of interesting. So in theory, if this, I mean, we could look at it through calculation now that we've got programs involved. If this is true, then we should be able to show it on the triangle. Let's try it out, just for fun. Okay, so this is let's assume the 0th row. That's going to be 1. It's going to be 2. This is going to be 4, 8. Looks good so far. Okay, we've got 8, 9, 10, 16. Yeah, these look like the powers of 2, right? Okay, and so... yeah, so we see it bears out there. And then there was something to do with the formula, I think. Now, what was it? It was... yeah, so... yeah, okay. So 2n... that's... we put that down. I think this was someone in the chat said this, or someone in the chat pointed me at this. I think I tried... oh, gosh, okay. That's weird. Didn't even know you could do that. Okay. Yeah. So this you can put 2n as 1 plus 1 n, and we know that the binomial theorem allows us to expand this, and so we can say then that we get yeah, we get the first term will be this. Yeah, so then this ends up being the kind of x in the scenario. Oh, let me put that underneath. This ends up being the kind of x. This ends up being the y. And so you end up being able to do something like this. You say xn, but that's really going to be 1n. And then this is going to be 1, 0, which is just 1. So we get to erase that. And then this ends up being 1 as well, because 1 to the power of anything is 1. Or something. Maybe I'm losing it. Okay, well that's... No, wait. Okay, let me just continue. Let me see if I get anywhere with this. Then it's 1 to n minus 1. And then 1 to 1. Which just ends up being 1 again. Yeah, I feel like I'm not quite... Not quite getting this, getting back to the point I was in. Or was it 2 plus 0? Was that it? Is that how I broke it down? No, because 0 to the power of anything would be 0. So that wouldn't work. Oh no, wait. It's the coefficients. That's what I'm missing. Yeah, okay. So basically all these terms end up being 1. I think. Yeah, the coefficients are what I'm missing. So it's actually... it's... Yeah, it's n choose 0. And then it's this all ends up being 1 as before. Yeah, and then it's n choose 1. Yeah, okay, I get it. It's come back now. N choose 2, etc. All the way up to n choose k. Because out of this, every term becomes 1. So we end up with like 1 here, or rather 1 on the, it should be 1 here basically. And then we end up with all of the choose terms added together, which is this thing we were asked to show. Yeah, this thing. So that's the kind of chain that we go on, right? I think. Yeah, I don't feel like I'm showing exactly. I feel like this is always like all these terms, no matter what this is, like that's the thing which yeah, so what the thing this hinges on is 1 1n for any n. All these powers are going to be integers. They're all going to be yeah, where it's like where n is a member of, I think this is the natural numbers. This is always going to be 1. I think that's what all of this. If we could show that this was true, I mean, we can kind of see it and see that it's true. But I suppose at some point it'd be good to properly prove that that's true. If that's true, then all of this holds up, because we know that in this expansion, all of these end up being integer. And I guess we should probably, binomial theorem. All of these are integers, basically. That's that's what I've got. Okay, I feel satisfied with that for where I'm at. That I've recalled enough. Okay, what's chat saying? Stephen Star 192 says it a different way. Basically, it's because each row is exactly 2z the previous row. Exactly 2 is the previous row, which is basically a consequence of its construction. It makes sense. Yeah, Bobbledon spotted my mistake. Now exercise 6 asked me to prove the same equality, but with the kind of math thinking would be super useful for the art of computer programming. My vids are recorded, so there's a VODs channel on YouTube which you can scroll down and see. The book at the moment is Book of Proof, but we'll be getting back to the art of computer programming after that. So we're on a kind of series. Thanks for the question, Han. Okay, so question 6. Question 6. Use definition 3.2 on page 87. Yeah, this 3.2 on page 87 and fact 1.3 on page 13 to show that the same thing is true. Okay. So this is the one Bubbledon thinks will be instructive. Okay. Let us see. Let us just find those. 85 and 13. Oh gosh, again. One window highlighted. Okay, we want to go to 85 and find fact 1.3, and we want it to go to 13 and find, no, actually that's wrong. Whatever's on 85 and whatever's on 13. Okay, and then we'll find out what those are. So 85, let's look. If n and k are integers, then n choose k denotes the number of subsets that can be made by choosing k elements from an n element set. Yeah, fine. Okay, let me just write this down somewhere. Okay, and page 13. If a finite set has n elements, then it has 2n subsets. That looks promising, doesn't it? Should have noted down the page we're on as well. 90 something. Yeah, okay. So, use definition 3.2. Let me find a way to put this on here as well. No, it's going to be nothing. Okay, definition 3.2. If n and k are integers, now that's this part we're thinking about there. If n and k are integers, then n choose k denotes the number of subsets that can be made by choosing k elements from an n element set. If n and k are integers, then n choose k, that's this part here, denotes the number of subsets that can be made by choosing k elements from an n element subset. So I think I remember that this, we thought about this previously, or I thought about this previously as like all of the elements of the power set. Let's make that somewhat fancy. The power set of a set of size, in this case n, so let's call this big N, where the cardinality of them, I don't know, let's say, terrible notation, I know, where the cardinality of x is going to be equal to k. That's what this says, I think. Or rather, it's talking about, this is a kind of equivalent. Or I guess it's the cardinality of all of this. All of the subsets, all of the sets in the power set of a set of size n, where the cardinality of the subset is equal to k, the number of sets in that set is going to be this number, which can be calculated, however we are interested in doing so. So that's kind of just loading that fact into my brain. Fact 2, if a finite set has n elements, then it has 2n subsets. If a finite set has n elements, then it has 2n subsets. So the natural place to try and join these together is, this definition that we're thinking about. If n and k are integers, then n choose k denotes the number of subsets that can be made by choosing k elements from an n element subset. N elements, sorry, I just had a thought there. Let me read that again. If n and k are integers, then n choose k denotes the number of subsets that can be made by choosing k elements from an n element set. And if a finite set has n elements, then it has 2n subsets. These feel quite closely mirrored statements, right? What do we do with that? Okay. All right. So let's look at, like, what we're looking at is we're looking at this. Let's get rid of this nonsense, rubbish. So we're saying that 2n is the number of subsets that a finite set can have. Number of, I'm just writing this down so I can think about it more. Number of subsets of a set of let's say size n. Okay, so we've got that. Now that's the right hand side. We've got this kind of links up, obviously. Now definition 3.2 is if n and k are integers, then n choose k, which is kind of related to what we're trying to work out here. Then n choose k denotes the number of subsets that can be made by choosing k elements from an n element set. So what I'm feeling is that, sorry, this is painfully slow. We're kind of joining all these together, right? We're joining all of the subsets of a set of size n that have k cardinality. That's what definition 3.2 is saying. So let me write this down as well. Thrilling stuff, I know. So this is number of subsets of size k that can be made from maybe a right, number of subsets of size k that can be made from a set of size n. And then this summing here, we're kind of joining all of the subsets of cardinality 0 through to n, and that's really like we're kind of, all this does is it's kind of partitioning. So if we took all of the possible subsets of a set of size n, there would be, so many with cardinality 0, so many with cardinality 1, so many with cardinality, in fact more, so many with cardinality 2, 3, 4, etc. And then it would, start to get smaller again or whatever. Terrible diagramming, I know. And then this summing here, this part, is us taking the size of all of these subsets, which is what we're calculating with with this and adding them together again. Which then gets us all of the possible subsets, because all of the subsets of a set of size n will have cardinality 0 through n and not outside of that. I happen to know. I don't know how I would show that, but I happen to know that just through knowledge. And then if we add all those together, we are going to get that all of the subsets of a set of size n, which according to the facts we've been shown, should be this number, which is 2n. I think that's as close as I'm going to get to showing that, I think. Basically, we know this number. We know this number is all of the possible subsets of a set of size n. We know that if we want to, we then take all of those subsets and we break them up into subsets of cardinality 0 through n, which we know we can do. And then we work out their size individually using this fact. And them being summed together obviously is going to be the same as the total number of subsets. So I think that's it. All right, what has chat been saying? Perfect. Okay, good. Okay, chat has been going off. Okay, Bubbledon a while ago says, what do you think of all the category theory after the raid last week? I actually loved the raid last week. The raid last week was great. I had a great time in that channel. It was like so different to all the other channels I've seen. I don't think our friend appreciated my comment on his tie quite as I thought the tie was amazing. The tie was one of the most amazing things about the stream. You never see it. I think it's the first time I've seen anyone wearing a tie on Twitch, but I hope not the last. I won't say I'd claim to understand any of the category theory though. But I feel like I will at some point. Yeah, notation a little off probably. Fortunately, I'm a software engineer, so I mean, notation. I probably don't need to. Not going to need to use notation so much in my life. Although it'd be nice to have it better. Great. Okay. Looks like I got something along the right lines of what you're expecting, Bubbledon. Stephen says, easy enough to see why the number of subsets is 2 to the power n. Imagine it's a binary number with a digit for each item in the set. It's either in the subset or not. So the total number of subsets is how many binary numbers are there with n digits? Oh, that's interesting, isn't it? See you, Bobbadon. Have a good dinner. Oh, wow. Fly. Yeah, interesting. Thanks, Stephen. Interesting point. Okay. Now, we're on to another exercise. 7. Use the binomial theorem to show the sum of k through n of... Whoa, okay. The sum of k through n for 3 to the power k n choose k is equal to 4 to the power n. Okay. Okay. Adrisa says, hello, by the way. I just want to say hi. Hello. Recently I discovered Concrete Mathematics by Knuth. I'm very bad at math, and for me it's black magic, but maybe someday I will learn. Yeah, I mean, it's not easy for me either, but tune in a couple of years and I'm going to be really good. Yeah, I actually do want to work through... I actually bought Knuth's Concrete Mathematics, but I haven't taken a serious look at it yet, but I hope to at some point. Because it'd be good to know his take on all of the prerequisites. Okay. Now, what on earth is going on here? Is this like number 5, maybe? Like we need to find a kind of expansion of this, which is then going to add up to this, maybe? Thanks. Enjoy lurking. Yeah, maybe. I mean, maybe 3k. Oh, okay, so k is a term for each sum, right? So, yeah, okay. Okay, okay, okay. Yeah. Alright, alright. So maybe we can do something like this. Okay, I need to just start that again. 1 plus 3 n maybe? And then it's going to expand to... So if this is the kind of x and this is the y of it, this is going to expand to... Yeah, 1 n 3 and then this will be... What's the whole theorem again? Again. We're going to have something here as well. Yeah, so it's going to be 1, yeah, n 3 0. And then it's going to be 1n minus 1, 3 1. Yeah, and then we're going to... Then we're adding from... We're kind of getting close. Now this is going to be n0. This is going to be n1. And then this is going to go through to... n. It's a cockerel, isn't it? n0, sorry, 1 0, and then 3 3n. So we end up with this, which looks a little close to what we're trying to get to. Oh, the dog is barking. This is the dog barking, in case you didn't know. Sometimes when people tune in, they're like, "Whoa, a dog's barking near in my location." But it's actually in. Actually, I don't even think this is the right attribution. I think I've just been attributing the sound wrong this whole time. No, this is the original one. This is the one I've just been attributing the sound wrong this whole time. Now, what is this supposed to be? This is supposed to be something else. Yeah, this isn't English countryside at all. This is just something. I'm gonna get rid of that. That's just got that wrong. Wrong attribution. Fortunately, it doesn't require attribution, but it's gonna be something else. It's gonna be, what is it gonna be? Yeah, it's actually this. It's actually that. Anyway, where was I? Focus. Okay, where were we? Yeah, so yeah, now if we were to expand this, need to learn to draw this character better. Yeah, if we were to expand this 3k, I was reading the other day that birds, including chickens, are, so you know how humans and mammals in general like if you have I don't know if I want to get into this even. Basically, birds, they have a set of they got different chromosomes, right? They've got different sex chromosomes. So they're like Z and W, and I think ZZ is female, ZW. No wait, ZW is female, ZZ is male, I think. So it's like the presence of a W chromosome that makes a duck female. Or any bird, I think. Any bird female. Which means like sometimes if a duck gets like the equivalent of like the thing that produces estrogen stops working, they default to male, and they acquire male characteristics, and so there are cases of ducks and chickens actually was where I was at. Chickens kind of transitioning, becoming cockerels or cockerel-like, especially if there's no cockerels in the area. That was pretty cool. Anyway, just the sound reminded me. Okay, so where was I? So this is going to expand to be 3, 0. In fact, let me sort that round. Swapping it around makes it even better. N0, 3, 0 plus N1 3 1 plus etc. NK or NN rather. No, wait. No, it will be NN because we're going up to N. 3N. Now we can get rid of all these ones because we don't need them because they're always going to be 1. And so as a result, if you kind of join these together, they're the same. So they're the same. I've shown they're the same, they're the same. They're the same. That's my proof. Am I streaming from a forest? No, I'm not. I kind of am actually. Not to dox myself, but I can see trees. Don't set the GeoGuessr guy on me and say there's trees around. Where are they? No, I'm not streaming from a forest, but there are. I have an audio bed, which I use to keep myself relaxed. And it's in Hungary. It's from it's from Hungary. This is not my audio, by the way. Let me put the proper location on. I don't know how to pronounce that in Hungarian. Pesel, Pest, Hungary. What it looks like. Gaming stream when? Yeah, I do think about it. I do think about doing a gaming stream. I do like video games. I was actually thinking of like I had an idea. If you're watching this and you think, wow, what a great idea. I wish I could do that idea. But Kay already came up with it, so I can't. You have my official license to do this. So you have like stuff in video games, right? A lot of video games are based on ideas drawn out of sci-fi. So there's like tech, there's like cool tech in video games sometimes. Noted example is Brendan in the video game Cyberpunk 2077, the sentient vending machine, or possibly sentient vending machine. Now, one of the cool things about Brendan is that when the game was released, that technology was futuristic. Now it is not futuristic. It is like somebody could build that. Somebody could build Brendan in real life if they wanted to. So the idea is take noted examples of technology or software, whatever, from video games and build it for real. That's the content, or the stream, or the video, whatever. I just think that'd be a great channel idea. It's not really, it's sort of semi on brand for me, but it's like not super on brand. So I haven't done it, and also it's probably quite a lot of work to do that. But I just feel like I would, if there was a channel like that, I'd watch the shit out of that channel, because, I mean, we kind of increasingly live in a world where video game technology can be real. So it'd just be cool to see someone making it real. Obviously, probably don't do it with the with the blowing things up technology. But, okay, so that's a much better content you could be watching right now if I'd chosen a different path. Okay, where are we at now? Next exercise. Again, always doing that. Let's get rid of that. Come on. Go up. Did that. Use fact 3.5 to derive equation 3.3. Really? 3.5 on page 87. Okay, if I click this, will it take me anywhere useful? Okay, well, let me write it down first. We want to go to We want to go to 87 and page 90, and we're currently on page 92. All right, let's see. Wow, we actually went somewhere useful. Okay, what are we supposed to be doing? This is fact 3.5. Fact 3.5 says if k is between 0 and n inclusive, then n choose k is equal to n factorial over k factorial by n minus k factorial. Otherwise, n choose k is 0. That's fine. I can copy that out. And then the other one we want to see is on page 90. That's this formula, right? We want to turn one into the other. Yeah, so on this one, okay, fact 3.5. So, yeah, we've got some conditions on fact 3.5. We've got if 0 k, can't draw lowercase k unfortunately, so why would you want to? Then n choose k is n factorial over k factorial multiplied by n. Yeah, we spent some time with this one before, didn't we? I seem to remember this. Yeah, otherwise it's 0. Let's say, okay. Now, we want to derive this kind of other thing. Let's go green. We want to derive, so this is our kind of target. n plus 1, choose k. Is equal to n choose k minus 1, oops, plus n choose k. Now how do we do this? Am I going to have to do some sort of crazy algebra? Maybe I did this one last time. Maybe I did this, it's possible I did this one last time. I did something along these lines last time. Okay, well we can just plug it in and see what we get. So if we have n plus 1, choose k, we can do n minus 1 factorial and then this is going to be, oops, that's not right, k factorial multiplied by n minus 1 minus k factorial. I don't particularly like this. There's probably something we can do with expressions like this that I vaguely don't remember, but I remember there's something you can do with that. Am I any closer to anything? I don't think so. I could expand the other side, maybe? Seems pretty horrible, but I could do it. Or actually, I'm supposed to derive equation 3.3. I'm actually supposed to derive equation 3.3. So yeah, so I think I'm starting in the wrong direction, maybe. Use fact 3.5. So this is fact 3.5. And this is equation 3.3. I don't think I'm getting anywhere with this. Do I have any ideas at all? I'm supposed to be able to essentially use fact 3.5 to break down this kind of choosing into two separate choosing expressions. So it's really Ren. Hello. It is a new whiteboard setup. It is. Apparently, harder looking side tends to be the easy one to get the answer with. Interesting. Okay. Since it does not say starting with X, you could show it starting from either side. Okay, so, right. Compare coefficients from the binomial expansion. Writing the left-hand side using 3.5 means you have a goal to reach using the right-hand side, if that makes sense. Compare coefficients from the binary expansion. Well, I'm not getting any really great ideas, but again. But this looks like kind of similar, right? Or maybe that just looks similar. Oh no. There's an interesting idea there. I'm not sure if it's the way I'm supposed to go about it, but in the triangle, right, we'd have the last two. Yeah, there's a existing triangle for this. We've got like this section. No, rather, let's look at like if only there wasn't this thing in the way. In fact, I have a tool for this. This is going to be 8 and 7. And then this will be like, 8, 8, whatever. That'll be 1, obviously. Well, that is interesting. I don't know if it allows us to derive to do this task, but it is kind of cool. I hadn't quite seen the fact in that way before. I guess that is this fact, right? And then we get the whole triangle out of that fact. Well, it is, and it's kind of interesting. Can I connect this to fact 3.5 in some way? If k is between 0 and n, then n choose k is equal to n factorial over k factorial by n minus k factorial. Oops. Oh, everything's in the wrong order now. Fine, whatever. We get the idea. Okay. Well, things make very gradually more sense, but I don't feel like I'm quite to an answer yet. Wow, it just went really quiet. Well, they're going to end up being equivalent. We've seen that. Wait, maybe we can get this another way. So the dog's back. I can't believe the dog's back already. So let's try this with some actual numbers, maybe. If we've got n and n, we're going to end up with n factorial over well, let's have k equals n here. In which case we're going to have n factorial over n minus n factorial. This then becomes 1, and these then divide out to get us 1. Then if we say k is n minus 1. I can't believe I left this dog in the edit. Okay, so in this case, we know we're gonna end up with n. No, we're gonna end up with n. We know we're gonna end up with n in this case because that's the way the triangle works. So to derive this, we've got n factorial over n minus 1 factorial multiplied by n minus 1 minus k. No, sorry, it's actually it's n minus n minus 1 factorial. Now in this case we know, so just let me keep this in mind. We know this is going to equal n. We know it's going to equal n because that's the way the triangle works. We know it's going to equal n. So we need to find, that's giving us a signal as to where we should be moving towards. So n minus n minus 1, I think this is the part of the expression that gets, it like shakes out everything. Or is that this part? So if this was like a real number, we'd end up with, let's say, 4 factorial over 3. And then this would end up being 4 minus 3 factorial, which would be 1. So that ends up being 1. And so we end up with 4 out of this. So yeah, so we end up with, how do we do that algebraically? Sorry, my algebra really is rusty. Too much cognitive load. So this ends up being plus minus n plus 1. No, wait. No, this is, yeah, n plus n minus 1. Oh my gosh, come on, Kay. Getting irritated at myself now for not being able to figure this part out. Okay, n plus n minus 1 is no, sorry, it's not that. That's where I got this wrong. It's minus k. Minus k. Yep, okay. I knew that wasn't looking right. N minus 1. It's the simple things. Okay, so we get n minus n plus 1. Wow, I just really can't. No, that is right. Yeah, so we just end up with 1, right? Which is what we expect, I think. So this ends up being n minus 1 factorial, and then 1 factorial, which is going to be 1. And so we then have, now n factorial over minus 1 factorial, that's going to be n by n minus 1 by n minus 2, etc. And that's going to be over, in this case, n minus 1, n minus 2, etc. So we get rid of all of those, and then we end up with n, which is what we expect. Okay. Great. I feel like I have a little more facility with that now. Now, can I apply any of this knowledge to my original task? Let's see. Come on, wake up. My whiteboard has exploded. There we go. A little better. Right. Let me get rid of all this too. Okay. So let's look at this again. Let's look at the left-hand side. N plus 1, choose k. And we know this is going to be n factorial over k factorial. And actually, now I think of this, I should have n plus 1 here. N plus 1 factorial. And then here we're going to have n plus 1 minus k factorial. And we don't actually need these brackets, I don't think, on this side. I feel like the solution may involve expanding, like treating this as a series. Yeah, so we're going to end up with, let's try this with the top bit. The k makes it kind of annoying, but maybe if we look at the top bit, we might discover something. So this is going to expand to n plus 1, n minus 1. That's an annoying notation, actually. Let me sort that out. N plus 0, n minus 1, etc. over this expression here, whatever that is. And because this is, because we've got multiplication on the top, right, we can separate these out. Or can we? What are the multiplication rules for fractions? Fractional expressions. You multiply the top and the bottom, right? Let me look that up. This is the level of mathematical facility I have. Okay, so you multiply the top and the bottom. Fine, great, but we've got to end up with an addition. So we can't break them up into multiplications. We've got to be able to break them up into an addition somehow. Fine. What's chat saying? It's Trillian has a tutorial to share after the question. Yeah, I would love that. I will let you know if you're still here when when I complete this question. Thank you. Okay. Come on, move up. Right. Right, okay, so where were we? We get that. It is an addition we want to turn it into, right? Yeah, it is. Yeah, it's an addition. How do we get an addition out of that? Weird. Well, it's an addition if you can make the top the numerators the same, right? Then you can do that. Then you could, if the numerators were the same, we could pull them apart potentially. But the numerators aren't going to end up being the same because we've got a k minus 1 on the left term. That's this one. Is there a way we can make them the same? Let me get rid of these actually. Don't think I need these anymore. Not that I can move anything around. I haven't got my moving things around tool on my on my whiteboard yet. We get this. Will these end up cancelling each other out, maybe? Maybe. Let's try this. So n and k minus 1. Oops. This ends up, we end up with, so we're now focused on this one. Don't lose focus. Focused on this one. Okay, so then if we wanted to express this using this, we would have n exclam over k minus 1 exclamation factorial, and then we've got n minus k minus 1 Now, with this, we need to, like, work out this bit. So n minus k minus 1, that's n minus k plus 1, right? Which is the same as n plus 1 minus k, which is this term here. So we've got that side. So that's kind of useful. We've still got this issue. Now, I feel like in this expansion, maybe there's something in that, like, so here we've got n plus 1 by n plus 0 by n minus 1. Here we've got these we can cancel these out, right? I know we can. We can cancel something out anyway. So we know k is less than or equal to n. Which means that k minus 1 factorial is gonna it's gonna trim off some factors in n exclamation mark, as is the one on the right, really. I'm on the right track. Okay, thanks Bob. All right, mental break to answer Lazy Schemer's question. Any advice for career changing to education? Would you recommend getting into academia? So I'm part of a couple. So my partner is an academic. So far, I wouldn't recommend getting into academia based on my partner's experience. Yeah, academia, I think if you wanted to switch into academia, and I've not spent loads of time trying to get into academia or anything, but if academia appeals to you because of teaching, like because of education as a vocation, I would probably try to lens in specifically on institutions which highly value education and teaching, because a lot of institutions, like their academics, are not there for that, really. Like they're there in a sense, they do teach and probably they get some enjoyment out of it, but that's not their focus, really. But there are some institutions that really do value teaching and see it as like almost a primary job, and people who go and work there are kind of that way inclined. So, and I think trying to get in with those people is always a good idea. I think I seem to remember Brown maybe was like that once, but I don't know if it still is. Anyway, these institutions are incredibly hard to get into in general, so it's hard to recommend going into them. But yeah, I would definitely recommend getting into private sector education for adults if you want to do education and you're technical. A lot of people do tutoring. Tutoring seems like a good education, but I don't think it's a real career. but there are careers out there for people who want to train adults, professionals, and I think it's a good line of work. My advice would be, I don't know so much about what you know, Lazy Schemer, but I guess you're probably in computing, judging by your username. And I don't know about your location, but there is a market for. What time zone are you in, Lazy Schemer? And what? Yeah, what time zone are you in? Australia. Okay. I was going to suggest you contact the company I work for, but Australia is so far away. Is it really Australia? Wow, I guess it is kind of the right time. Yeah, I would be looking for organisations that do specifically training for engineers. There are quite a few out there for software engineers. I mean, and they all work in different ways. But what I will say is that there are a lot of organisations who value ex-industry people or current industry people doing training. So it's actually kind of easy to get into if you have a high degree of technical skill, to get into education and then learn from that point. Like there are organisations, definitely in the UK at least, and I think it's a phenomenon globally, where they will look more for technical skills than educational skills, and then you have to make sure you get the educational skills yourself, or hope you're in an organisation that values those things. So, yeah, if you want to reach out via email, feel free to do so. Happy to talk further about it if you want to. I won't ask you to share any more personal details on stream, but if you want to share any more about where you're coming from and any organizations you think maybe look good or don't look good, do get in touch, because it is something that I know stuff about, and I'm also excited to help people with, because it's an interesting career path. Would recommend if you like the human brain and you like technical details and you're willing to try to be better than everyone else, technical education is a great field to be in, because it's very easy to be average at, but the rewards of being great at it are really really high and really meaningful. Okay. How many people have I bored off the stream at this point? Let's see. Okay, we're doing okay. All right. So, how's my coffee doing? All right, I'll get to the end of this coffee with this problem, and then let's see. I do feel, although it's slow going, I feel like I'm being rewarded for my efforts in understanding this a bit better. Glad I came back to these exercises, even if I only do these exercises at all today. Okay. So, now here's something, right? If we have n factorial and we've got n minus 1 factorial, then this is going to be n, because we're chopping off all of these things, all the things that would be here. And if we've got minus 2, it's going to be n by n, or n squared. So, if we have n over k factorial And we can say that k is less than or equal to n, then we can probably do something like this maybe. We can say n by n minus 1 factorial and k by k minus 1 factorial. Well, I guess that will have to be... No, actually, it'll be like this. We can kind of expand bits off of this is what I'm saying, and maybe we can remove bits like that. Now if these were equal, we could just take these out. But we know they're not, or we don't know that they are, rather. We know at some point they're not going to be. So there's some operation there that we can do something with. Yeah, I don't think we need this right now. If we can show these two things are equivalent, I think I'll be happy. We can assume these k's are the same, maybe, I think we can. Or these k's are these k's are a bit iffy, actually. N k minus 1. This is n plus 1 k. And I suppose we may as well do the work of getting the other part done, right? This is just going to be the same, isn't it? Same as the fact 3.5. But good to have it here anyway. We could just try and multiply them together. It does sound like it would be horrible. Or it looks like I don't want to do it, basically. Then again, actually, now I think of it, it might not be that horrible if we think of it as like... If we think of it kind of like treat it as a bit of an expansion. Though we're not going to multiply them together because you don't need to. That's not what we're going to do. We're going to add them together. do something with this. This is going to end up being where's my orange? There we go. N minus k plus 1 factorial. And this will also end up being that. N minus k plus 1. Terrible k there. Let me actually rewrite this whole thing. Okay, n minus k plus 1 factorial. Let's think about this term some more, maybe. So what we're talking about here is like n minus 1, n minus 2, and we divide out a certain fraction of these, and it's going to be all of the so let's say if we had, I think I did this before already. Ugh. For 2 we get 4 factorial over 2 factorial. Again, I should choose something different. Let's go 5, 3. And then this ends up being 2. Sorry, there needs to be 5 here. And so we then have, like, if we expand this out, it's 5, 4, sorry, 3, 2, 1, multiplied by 3, 2, sorry, it's divided by 3, 2, 1, and then 2, 1. Which means we take this out this out, and this out as well, we end up with 2, so 20 over 2, 10. Is 5 choose 3 actually that? No, no, I think of it. Should check that, double check I haven't made any silly mistakes there. It is. So we're taking out all of the terms from k downwards. So we're chopping off the early part of the factorial. And then we're doing it again with this. Stuck again. Stuck again. Yeah, proof by induction is the goal. It's odd because this book is sequenced so that these questions don't require proof by induction, because the proof by induction comes later. So in theory, the textbook's designed not to be read, I think, anyway. There is a how to use this book section to not require anything further on. In principle, anyway. Maybe if you're better at algebra than I am. Where were we? Here we are. Okay. I think I'm admitting defeat on that one. Come on. Highlight for me, please. I'm admitting defeat on that one. I've kind of reached a stopping point on anything I can think to do with this. Like, I guess the only other thing I could do would be to just do like a bunch of heavy examples. Like, I could just try and puzzle through like a number of examples of it. Yeah, let's do that. That's fine. Why not? I mean, something to do, isn't it? Probably learn something in the process. Come on. There we go. Okay, let's look at equation 3.3 with a bunch of examples. So, okay. Let's say we've got 4 plus 1, and we're choosing 3. This is going to be equal to 4, choose 2, plus 4, choose 3. Now let's use the 3.5 to just expand this out on the right and the left actually. Let's just try and do both. Okay, so we're going to have 5 over, oh, terrible drawing, over 3, as before. This will be 5 minus 3. And then here we're going to have 4 over 2, exclamation mark. And then we're going to have 4 minus 2, I think. Yep. And then we're going to have 4 exclamation mark again over 3, 4 minus 3. Now if we were to expand this out, we would get, I'm just going to write down the digits just for speed now. 5, 4, 3, 2, 1 over 3, 2, 1. No, wait. Maybe I won't do that actually. Let me just do one more thing. Three exclamation mark. Now 5 minus 3 is 2. Now for this, we've got 2 exclamation mark 2 plus 4 factorial over 3 factorial, well, 1 factorial. Which is kind of interesting, because we've got like a kind of correspondence, as you would imagine, I guess, here. I'll just expand these out. I might look at another example after that. So 5, 4, 3, 2, 1 over 3, 2, 1, 2, 1, 4, 3, 2, 1 over 2, 1, 2, 1. Come on. Wow, really lagging today. Okay. 4, 3, 2, 1 over 3, 2, 1. Now, what I notice is if we cut this out and this out, or rather, if we multiply both we multiply both sides by 2, we multiply both sides by this term, we get rid of this, this, and this. And then we've got 4x clam over 2x clam plus 4x clam over, sorry, 3, I guess. Or another way of putting this, we've got this, which is this. Just sort of interesting. Don't know if it takes us anywhere. I wonder how we get out of all of this like a 5. We don't need an extra 5 on there, don't we? Verilic says, try making the denominators equal. And what would they do if they were k minus 1 x clam and k x clam? What would you do if they were n minus k plus 1 and n minus k? Yeah, if we could make them equal, then that would help for sure. And this is a custom whiteboard, by the way, not Vukik, but it's based on a similar library that TLDraw uses, in case you want to take a look at TLDraw. Shorthand says, use the summation to 2 to the power n on both sides, and prove it using the definition of 2 to the power n plus 1. Choose n k plus 1 is the same as choose n1, picking the exclusion instead. That's true. We haven't looked at haven't looked at the binomial theorem in a while, and this is the exercises for the binomial theorem specifically, so it should come up right. And somebody mentioned that earlier, so worth looking at that again. So, right. So we've got we've looked at the earlier part of that before. Oh, the dog's back. It has been a while on this problem, hasn't it? Okay. Use the summation to 2 to the power n on both sides. Which is a fact we looked at earlier, right? I mean, the rows in the triangle looks like it ends up being 2 to the power n, though we don't have all the terms, so that doesn't necessarily help us immediately. All right, I'm giving up on this problem. This problem is too hard for me right now. Hate to admit it, but it is. Okay. Regrettable. I will come back to it. It's really ran. I appreciate it, but I think I won't in this case. Take a look at your solution, but I will, as I intend to come back to it because it's bugging me. But when I do it, I would love to see your solution. I'm going to mark this as yellow, and I'm going to move on and look at this one. Now, are there any that don't look horrendously difficult that I can do before I go on a break? I guess they probably all get a little bit harder from here. Okay, let me take a look at some of these. Use the binomial theorem to show n choose 0 minus n choose 1 plus n choose 2 minus n choose 3, etc. equals 0 for all n for n greater than 0. What's this term doing? This term is... Oh, right, okay, so we're kind of taking the powers of minus 1. So in this case, like, if we think about the triangle... Oh, again? Let's use a nicer color. We have 1, 1, 1, 1, 2, 1, 1, 3, 3, 1. Now, let's map in some 1s and -1s to this. So this is going to be a plus, minus, plus, minus. This is going to be a plus, minus, plus. And this is going to be a plus and a minus. And this could be a plus. This one doesn't count because we don't care about this one. This one's not in the guards we care about. And then if we do this, plus, minus, plus, minus, plus. And then this is going to be 5, 10, 10. So we can sort of see that it is. It's kind of, it's relatively obvious for the, it's relatively obvious for the even numbered, for the odd, no, for the even numbered ones, because you can sort of see they end up alternating, right? Which makes sense. Now for the odd numbered ones, we've got 1, -4, +6, -4, +1. Do we do anything with that? Let's try with this row. This row is a little easier. Now with this row, we can see that this one and this one add up to this one. With this one, it seems more complicated. With this one, we've got +6. And then these, obviously the negative terms are going to add up to 8, -8. And then we've got this as well. So how do the odd ones work? That's the interesting question. Okay, don't think I'm going to get anywhere interesting with that one either. I think these show ones are getting a bit too tricky for me. Come on. Oh my gosh. Software these days. Okay, show that the formula K, yeah, fine. Okay. Yeah, I think these ones are probably too tough for me right now. I think I just need more. I think I need better tools than the ones I have at the moment. Probably I could get lucky with some of them. There's that fly again. Okay, maybe the last one. The last one's usually pretty easy. The first 5 rows of Pascal's triangle appear in the digits of the powers of 11. 11 to the power 0 is equal to 1. 11 to the power 1 is 11, 11 to the power 2 is 121, etc. Why is this so? Who knows? Okay, alright. Those I'll have to come back to. Disappointing, but there you go, that's learning for you. That's why they're there, to cause problems. And then we were looking at these as well. Yeah, so I think we'll do some of those. Let's do. I don't want to go on my break, having been totally unable to do the last few problems. So let's see if I can get a good one, get a solution to something before I go and make another coffee. Okay. At a certain university, 523 of the seniors are history majors or math majors, or both. There are 100 senior math majors, and 33 seniors are majoring in both history and math. How many seniors are majoring in history? I think I'll make that bigger. Wow, come on. Terrible circling. Wow. Okay, come on, there we go. That's a bit better. Well, I'll have to do. Okay, let's call this math, and this call history, and this is M plus H. No, it's M intersection H. And then the whole thing is M union H. Now, what's our question? How many seniors are majoring in history? So we want to know what the size of H is. And we know that M union H is 5, 2, 3. We know that there are, this is going to be 100, this whole circle here. And we know that 33 seniors are majoring in both. So, in fact, let's put this in here. This is going to be 33. And we want to know what H is. Okay, and we have a formula for this, right? Inclusion-exclusion formula. So we know that... Oh, should have the cardinalities on here. Terrible. Etc. Okay, so we've got 5, 2, 3 is equal to 100 plus, let's say, H minus the intersection, which is 33. And we want to get H. So we could do a bunch of maths. Do a bunch of maths. Okay, let's say we add 33. That's not a 3. And that's going to get us, so 5, 2, 3 plus 33, 5, 5, 6. Yep, and this is going to be h plus 100. And, sorry, plus 100. Come on. And then we subtract 100 from both sides. And we're going to get 4, 5, 6 equals h. Does this make intuitive sense? I think so, yeah. Yeah, so if h is... Oh, there's that dog again. If h is 4, 5, 6, and... Yeah, if we then subtract the 33 and add 100, we should get this number. Let me try that. Okay, we get the right. Okay, we get the right answer. So the right answer is this. Okay, some success. Some success at least. All right. Okay, exciting stuff. All right, I'm going to take a short break, and then I'm going to be back in maybe 3 to 5 minutes. Let's see. See you in a sec. I have returned. I got Dashwater. Not sponsored by, but if Dashwater would like to send me any crates of Dashwater, I'm very happy to recommend them. Just can't resist a Dashwater. Okay, alright. Wow, this has been rough. Still, the whole point of this whole project is, what does it take? What does it take as an everyday maths loser to acquire the necessary knowledge to be able to do all of this stuff? Well, you're seeing it. You're seeing it here today. All right, let's do some more easier problems. Let's see if we can make any progress on this. All right, number 2. How many 4-digit positive integers are there for which there are no repeated digits, or for which there may be repeated digits, but all what? All digits are odd. Okay, great. Thank you very much for this question, Richard. Wow, I am terrible at drawing. See, this is why I need the simplification on. Okay. I'm going to work on some better circle tools for next time. So painful even to watch. Okay, how many 4-digit positive integers are there for which there are no repeated digits, or for which there may be repeated digits, but all digits are odd? Okay, so let's say we've got here repeated digits, or for which there may be repeated digits, but all digits are odd. Sorry, no repeated, that's right. No repeated. All odd. And this section here is where we can where there are no terrible, no repeated and all odd. And we want to get the size of the kind of union of these spaces, these categories, these sets, which means we need to have some formula for one. Let's call this one n maybe, and this one O. So the cardinality of n for no repeats. Now there are 4 digits for which there are no repeated digits. So this is going to be, how many ways are there of selecting of choosing. It is choosing, I think. So it'll be, do we need to worry about zeros here? I don't think we do. They have to be 4 digits. No, they do have to be 4. They have to be 4 digits, so they can't just start with zeros, because that's going to be, a problem. Because in this set, like 0024 is not a 4-digit positive integer. This is going to be, we're going to count this as a 2-digit positive integer, right? Although, I suppose in this case the only valid one would be this, but still, we can't have that. So we're actually going to be choosing between 9 digits here and then 10 digits here. Right. So I'm reluctant to use choice anywhere actually. So I'm just not sure it will behave correctly. But in this case, we're going to have we're going to have 9 to start with. And then even if we choose 1 there, we're going to only have 9 choices left. If we choose 0 here, we're going to have 9 choices left. So I think we have 9 again. Although actually, if we choose 0 here, no, we still do have 9 choices left. So it's going to be 9, then 8, then 7, I think. I think that's right. Okay, so that's that, but that's not yeah, this is with no repeats. So I think that's, yeah, I think that's the number of digits where the number of 4-digit positive integers for which there are no repeated digits. Now, the size of O of the odd where no, they're not yeah, where all digits are odd. So zeros are discounted already. So the odd digits are going to be 1, 3, 5. Awful. Wow, I don't know if anyone else's brain works like this, but my brain just really struggles to do basic tasks. Which is you'd think, given the things that I managed to do, that I would possess some measure of cognitive ability, but it does seem to abandon me at times. Okay, so that's 5 possible digits, and there can be repeated digits, but all digits are odd. So it's like we get to choose between 5 digits, then 5 again, then 5 again, then 5 again. So yeah, the result ends up being that. And then we want to use this formula, right? We want to say the union of these two sets is going to be the cardinality of, or the size of one plus the size of the other. Probably shouldn't have chosen O now, I think of it. Minus the intersection. So we need to work out the intersection separately, because we don't have a system for that right now. So in intersection O, that's going to be all of the numbers where the digits are all odd and they're not repeated. So that's going to be 5 by 4 by 3 by 2. Let's work out these numbers. So we got 5 by 4 by 3 by 2. That's 120. Then we've got 5 by 5 by 5 by 5. That's going to be 625. And then we've got 9 by 9 by 8 by 7, which is going to be 4, 5, 3, 6. And so our result of N union O is going to be 4, 5, 3, 6 plus 6, 2, 5 minus 120. Now, what is that going to be? 4, 5, 3, 6 plus 6, 2, 5 plus, sorry, minus 120. Okay. And that is a very suspicious number, 5041. Interesting. Okay, cool. Hello, Decker. I'm well, thanks. How are you? Yeah, I've this stream has been a tough one mentally. I struggled again with some algebraic problems, and I was defeated today. Okay, 3. How many 4-digit positive integers are there that are even or contain no zeros? Okay, I don't think we get to use any of the previous working. Even or contain no zeros, so we're looking at the 4-digit positive integers. Let's call that A. Then it's a union B. So we want to work out the cardinality of A plus the cardinality of B minus the cardinality of a intersection B. Now, cardinality of A first. That's integers that are even, 4-digit integers that are even. Now, what this means is that we get to choose. So we don't care about duplication or anything. So we can choose between 9 digits at first, and then we can choose between 10 digits because we have 0 allowed. Then we can choose between 10 digits again. And the last digit we can only choose 0, 2, 4, 6, or 8, one of 5 digits. For the size of B, we have, what do we have? contain no zeros. Seems relatively straightforward. So for that we've got 9, 9, 9, 9. And then we've got A intersection B. That's all of the positive integers that contain no zeros, 4-digit integers. So that's, we get to choose between 9 digits to start with, then 9 because we remove 0, then 9 because we don't have 0, and then the even ones we exclude 0, so we have 4 to choose from at the end. So the result, this is going to be 9 times 10 times 10 times 5. That's 4,500. Nine to the power 4. 6561. And then 4 times 9 to the power 3, which is 2916. Six. And then we've got 4,500 plus 6561 minus 2916, 8145. Okay. Decker says, because of your earlier streams, I got motivated to learning maths. That's great. I'm so happy to hear that. Welcome to the Terradrome. Just by asking AI, it said, based on some searches, just asking AI, it said different fields needed different types of maths: linear algebra and geometry for visual, linear algebra and calculus for machine learning, discrete mathematics for computer science. I don't know anything of maths here. Every topic requires its prerequisites, and that require its own prerequisites. Is that the correct way of looking at it? We've already got a response from It's Really Ren. If you have something you want to learn in particular, it's probably best to just jump straight in. The only prerequisite you probably need to know is how fractions work, how to manipulate algebra. Maybe some pre-calculus stuff would be nice, but mainly just practice is the way you get better. There are probably tons of curricula online out there too. I think that's a great answer. I'll only add one thing from more of a educational perspective. So your key resource as a learner always is not it's not learning resources. It's not even really teachers. It's motivation. Motivation is your key fuel that you burn in the course of learning. And so anything that helps you maintain your motivation is really, really important. So some people are massively motivated and they find this thing's very easy. Some people are not very motivated at all, and some people like me are kind of in the middle. I think I'm my constructed motivation is higher than my intrinsic motivation, let's say. And there are kind of there's a kind of brake and accelerator on motivation. The accelerator is how exciting you feel the work you're doing is. So working towards, just sort of as It's Really Ren says, just diving into the stuff that really excites you. And if you can then do it, it's great. Similar to programming, right? if you're working on stuff that excites you, then it gives you a lot of motivation. That dog is... I've heard that dog too many times now. So that really motivates, and it's a good reason to just not worry too much about prerequisites. However, one thing that really saps your motivation is if you don't understand what you're doing and you can't make any progress on the things that excite you. It tends to make people feel kind of, stupid, and I'm no exception to that. And this happens often if your prerequisites are not strong enough. So you dive into the things that excite you, think, oh, amazing, I'll do this stuff. And then you're like, wow, I don't understand any of this. And the prerequisites are so, that the missing knowledge is so dense in what you're trying to learn, you kind of lose your motivation and you kind of struggle. So you want to strike a balance between the two. You want to have, keep really strongly in mind where you want to go and keep probably trying to test yourself against problems that you're interested in, but also be realistic about the fact that the prerequisites are also going to be important, and if you don't have enough of them, then you're going to need to go back and work out what you need to learn. One thing I would suggest not doing is simply starting at the beginning, because your motivation is probably not going to fuel you all the way through. You probably want to start somewhere in the middle and maybe jump back and forth between exciting, interesting problems you probably can't do, and smaller, simple problems that you can do, and which will help you build up towards more complex things. So definitely don't look at it as totally a skill tree where you just work, up from the very beginning, unless you're really you've got good experience of making that work. But also, keep in mind that prerequisite knowledge will definitely help. And if you find yourself like thinking, wow, I don't understand any of this, then try and drop it down a notch, and see if you can understand any of the lower level knowledge. And good luck as well. I'm here for you. I'll be here for you for a while, doing my own version of that. What a cool mission in Deca. That's really exciting. Biological simulations and patterns, generative procedural visualization, really cool. Okay. This problem involves lists made from the letters theory with repetition allowed. How many 4-letter lists are there that don't begin with T or don't end in Y? Will I do this one? How many 4-letter lists are there in which the sequence of letters... Okay, I think I know that stuff well enough. Let's try out number 5. How many 7-digit binary strings begin in 1 or end in 1 or have exactly 4 ones? Okay, let's do this one just to get the feedback on the answer. So, right, begin in 1. 7 digits. So that's really the number of 6-digit binary strings, right? which will be 2 to the 6. Ending in 1 is the same. Or have exactly 4 ones. Oh no, wait, I'm not even doing that. Let's get C up. All have exactly 4 ones in a 7-digit binary string. We don't know where they are though. But we're going to have to work out some horrible intersections here. Okay, if they have exactly 4 ones, then we are choosing the other 3 digits. So we've got 2 to the 3 multiplied by maybe the positions. We could look at the positions. Can we do that? Let's say we've got 7 spaces. Okay, and let's say we pick, oh no, exactly 4 ones. Now I think of it. That means they have 3 zeros. So actually, what we're choosing is the positions of, yeah, the positions of the ones, and all the rest are zeros. So we get to choose 4 positions from 7, right? So is it 7, choose 4? Choices can't have repeats in them, I don't think. We've got a book link. Damn, that looks like a cool book. Yeah, cool book. I think that one is, yeah, definitely going to be amenable to a working through with like AI assistants maybe approach. Yeah, they might be able to, probably the AI will be able to point you to good prerequisites for that, which will help you out when things get a bit rough. Plus everything It's Really Ren said as well. Okay, where were we? How many 7-digit binary strings begin in 1 or end in 1 or have exactly 4 ones? Yeah, okay. So then we need to work out A intersection B. Now that's going to be all of the ones that start and end with 4 ones, with a 1, which means the number of bits left is going to be 2 to the 5. Then we've got to have A intersection C. Let me just double check the formula for this actually. Yeah, it's like a... Yeah, we need to work out all the intersections. Yep, okay, and A intersection C, that's the ones that begin with 1 or end with 1. No, begin with 1 and have exactly 4 ones. Now that's going to be... What's that thing again? That's going to be 6 choose 4. No, wait. 6. If it begins with 1 and it has exactly 4 ones, it's actually 6 choose 3, because we've already got a 1 there. Then we've got B intersection C, which is going to be 6 choose 3 again. And then we've got A intersection B intersection C. Now that's going to be all of the strings that begin in 1 and end in 1 and have exactly 4 ones, which is going to be... Maybe I'm missing something here. No, it's exactly 4 ones, so that all the others are 0, so there's no other combinations to be had of those strings. So this one's going to be 5, because we've got the beginning and the end set for us, so there's only 5 bits left, and we only have to choose 2 because we've already got 2 bits in there. Okay, and then we've got this horrendous thing here. Now this is going to be... Let me just work all these out. 2 to the 6 is 64. Let me just double check that. It is. Amazing. Okay, 7 choose 4. Seven choose 4 is allegedly 35. Two to the 5 is 32, as we discussed earlier. 6 choose 3 is 20. 20 again. 5 choose 2 is 10. Actually, we did look at that earlier, now I think of it. Or was it 5 choose 3 we looked at? Anyway, same thing. Okay, and then we want to have A union B union C. And that is going to be 64 plus 64 plus 35 minus all these intersections, so that's minus 32 minus 20 minus 20 plus 10. Okay, let's work that out. 64 plus 64 plus 35 minus 32 minus 20 minus 20 plus 10. 101, allegedly. Now, does this make sense intuitively? What's the question again? 7-digit binary strings, of which there are 128 that begin in 1, or end in 1, or have exactly 4 ones. Does seem like a lot, but it could be true. Well, we'll find out soon enough. Oh, and Decker, I just noticed your comment about 3 blue, 1 brown. Well, how's the enriching discussion in the chat going? Yeah, cool. A lot of stuff about visualization. I don't fully understand 3 blue, 1 brown videos. A lot of people praise, and I understand why, but I don't feel like I learned anything. Yeah, that is fair. I think they are, I think I actually watched another video recently about that type of channel, and it's probably best to describe it as like a motivational channel. It's a channel that makes you either, maybe if you already know all that math, it's like you probably already hits real different, but for the rest of us, it's like it would be cool to be able to understand this type of content. Okay, let's look at another exercise. Is the following statement true or false? Explain. If A1 intersection A2 intersection A3 is the empty set, so they don't intersect in the middle. So yeah, so let me... So we've got a circle, where it doesn't have to be a circle, but let's say they could, let's say that we could have these sets that maybe they could even intersect with each other, all of each other, but they don't have any intersections together. There's no intersection right in the middle of these 3 sets. Then A1 union A2 union A3 is equal to the cardinality of A union of A1 plus A2 plus A3. That seems wrong. Yeah, so it's basically saying if 3 sets have no intersection between all 3 of them, then the union of all 3 of them must be the sum of all of the cardinalities, which I don't think is true, because you could have an intersection, like you could even imagine, for example, like 3 sets like this. So these 3 sets, they have no intersection between all 3 sets, right? But clearly the cardinality of this plus the cardinality of this plus the cardinality of this is going to overcount everything in here. So, no. It double counts, or it could double count. For example, A1 intersection A2. So I think no. False. Not that we get the solution to this one, but still. Okay. What have we got in number 7? Consider 4 card hands dealt off a standard 52 card deck. How many hands are there for which all 4 cards are the same suit, or all 4 cards are red? I think I'll skip that one, that doesn't look too hard. Consider 4 card hands dealt off a standard 52 card deck. How many hands are there for which all 4 cards are of different suits, or all 4 cards are red? Just seems, I think I have the knowledge for that one, but it seems like arduous. A 4-letter list is made from the letters listed according to the following rule. Repetition is allowed, and the first 2 letters on the list are vowels. All the list ends in D. How many such lists are possible? Let's try this one. Okay, repetition is allowed, and the first 2 letters on the list are vowels, or the list ends in D. So we've got, and we want to work out A union B. So I think basically the logic is going to be, well, we apply the same thing. So let's look at the cardinality of A. Repetition is allowed. First 2 letters on the list are vowels. There's only 2 vowels in there. But they can be repeated, and they can come in either order. So we have 2 choices at first, I or E, and then we have 2 again, and then we have 6, and then 6, and then for the cardinality of B, we've got all the list ends in D. Okay, so in which case we've got 6 letters to choose from, 6 letters to choose from, 6 letters to choose from, and that's it. Then we need to work out A intersection B. Now that's going to be the first 2 letters on the list are vowels. So we've got 2, then 2. I assume this is an inclusive OR. We should probably assume that. And then we've got 6, and that's it. Because the list is going to end in D. We don't get a choice in that. Okay, and then for this, we want to do the whole formula thing. So it's going to be 2 times 2 times 6 times 6 plus 6 times 6 times 6 minus 2 times 2 times 6. That's 336. Okay, that seems fine. All right, number 10. How many 6-digit numbers are even or are divisible by 5? Fine. How many 7-digit numbers are even or have exactly 3 digits equal to 0? Yeah, I think that one's fine. How many 5-digit numbers are there in which 3 of the digits? Yeah. Okay. How many 8-digit binary strings end in 1 have exactly 4 ones? That seems fine as well, but deceptively fine actually. So I'll probably do that one. Okay. 11. No, 13. 8-digit binary strings ending in 1 all have exactly 4 ones. Same thing again. Now a 8-digit binary string ending in 1 is a 7-digit binary string. That's 2 to the 7, 2 to the 7, 2 to the 5 is 32, 64, 128. Let me triple check that. No, it's not. No, it is. It is. Okay. B. Exactly 4 ones. So we're choosing from 8, we're choosing 4 positions to make ones, right? So 8 choose 4. I don't want to install a new terminal now, thank you. That's 70. Thanks, this is really Ren. Have a great day. Thanks for hanging out. And then we've got A intersection B. And that's going to be, what is it going to be? We're going to be all of the binary strings that are 8 digits long that end in a 1 or have exactly 4 ones. So that's going to be 7, choose 3. Which is 35. And then we do the same work again. It's getting kind of dull at this point, isn't it? 128 plus 70 minus 35, 163. Yeah, I'm starting to feel these are dull, and then I'm just going to come to the answers, and it's going to be they're all going to be wrong. Okay, where are we at? 13. How many 3-card hands have the property that it is not the case that all cards are black or all cards are of the same suit? And then number 15 is how many 10-digit binary strings begin in 1 or end in 1? That one looks dull. 14 looks sort of interesting, but we won't get a oh, okay. Okay, that's interesting. We won't get a answer to that one, but let's try it anyway. Okay, how many 3-card hands have the property that it is not the case that all cards are black or all cards are of the same suit? So we could work this out. by calculating the cardinality of the universal set, and then we could say our answer, which we will have as, I don't know, x, is going to be the cardinality of the universal set minus our A union B set. So we need to work out this, and then we need to work out A, and then we need to work out B, and then we need to work out A intersection B. And then we need to work out A union B. You can tell I'm getting tired because my handwriting is getting worse. Okay, so universal set, 3 card hands from a 52 card deck. Now these will be without. These will be with replacement, right? No, without replacement, because they're hands. So it'll be 52 by 51 by 50. Or I suppose we could have it be 52 choose 3. Probably easier. Yeah, 52 choose 3. Then A is going to be, come on. A is going to be, what is it? All the cards are black. So if all the cards are black, that's going to be 26 choose 3. Because 26 black cards in a deck. Now, the other one is all cards are of the same suit. So we could then choose, we could say we pick the suit, which is 4. And then we could say 13, choose 3. Intersection B. That's where all cards are black and all cards are the same suit, so that'll be 2, 13 over choose 3. And then the union will be, apply the formula as before, and we'll get the result. So let me just calculate that out. We won't get an answer to this, so we don't get to find out whether I've got it right or not. 26 choose 3 plus 2 times 13 choose 3 minus, sorry, it's actually 4 times, minus 2 times 13 choose 3. That gets us the A union B, which is 3172. And then the universal set is 52 choose 3, which is 22 100. And then we subtract out 3172. And we get the answer of 18928, which who knows if that's right, but it seems roughly right. How many cards that are not Not all black and not all cards of the same suit. Yeah, seems roughly right. Well, there's not even more. Okay, let's take a look at the answers for this. What section are we on? 3.7. Okay, I think I deleted all of my answers to the previous one. I rage quit. I think I was right. That seems familiar. I think I got that one. Yeah, I think I got this one. That one I didn't get. We'll look at the others another time. Okay. Let's start from the end and move backwards. We didn't do 15. 13, 163, correct. 9, 336, correct. Oops. I didn't do 7. I did do 6. 6 was fun. 5, 101, that's correct. 3, 8, 145, that's correct. I did 2, 4, 5, 6. Okay, that's right. Good. Okay, well, I got something right today. It's reassuring. Reassuring I'm not completely useless. Okay. Counting multi-sets. Okay. Let's check out the next chapter, shall we? Okay. You have in your pocket 4 pennies, 2 nickels, a dime, and 2 quarters. Uh-oh. We're in American money now. I'm not going to be able to do any of this. I don't know what any of those words mean. You might be tempted to regard this collection as a set, such as this. I suppose that's what they are. Let me try and load this into my memory. A nickel is 5 cents, a dime is 10 cents, and 2 quarters. Well, a quarter I guess makes sense. But this is not a valid model of your collection of change because a set cannot have repeated elements. To overcome this difficulty, we make a new construction called a multiset. A multiset is like a set except those elements can be repeated, except that elements can be repeated. We will use square brackets instead of braces to denote multisets. For example, your multiset of change is etc. Okay, so we don't care about order still. So it's not a list, but it's a set that can have multiple elements in it. Okay. A multiset is a hybrid of a set and a list. In a multiset, elements can be repeated, but order does not matter. For instance, yeah, given a multiset A, its cardinality is the number of elements it has, including repetition. The multiplicity of an element x in A is the number of times that x appears. Multiplicity, okay, great. What a delightful word. So the element 1 in the set A has the multiplicity 4. Yeah, fine. Notice that every set can be regarded as a multiset for which each element has multiplicity 1. In this sense, we can think of the empty set equaling this as the multiset that has no elements. To illustrate the idea of multisets, consider the multisets of cardinality 2 that can be made from the symbols A, B, C, and D. They are those. Okay, so they're allowed repeats. fine. I suppose if you don't restrict the cardinality, then they can have infinite size. We have listed them so the letters in each multiset are in alphabetical order. Remember that we can order the elements of a multiset in any way we choose. And the 10 multisets are arranged in dictionary order. For multisets of cardinality 3, made from these, we have all of these. Though this set here has no subsets of cardinality 5, there are many multisets of cardinality 5 made from these elements, including exactly how many are there? This is the first question about multisets we shall tackle. Given a finite set X, how many cardinality K multisets can be made from X? Okay. Let's start by counting the cardinality 5 multisets made from symbols A, B, C, and D. Our approach will lead to a general formula. We know that we can write any such multiset with its letters in alphabetical order. Tweaking the notation slightly, we could write any such multiset with bars separating the groupings A, B, C, and D, as shown in the table below. Notice that if the symbol does not appear in the multiset, we still write the bar that would have separated it from the others. Okay, fine. So we're probably going to choose the location of the bars, right? Maybe? But they can be in multiple places. Or you can have multiples in one place. This suggests we can encode multisets as lists made from the two symbols asterisk and bar, with an asterisk for each element of the multiset as follows. Okay, interesting. Star for each A, star for each B, star for each C, star for each D. Okay. For examples, see the right-hand column of the table. Any such encoding is a list made from 5 stars and 3 bars. So the list has a total of 8 entries. How many such lists are there? We can form such a list by choosing 3 of the 8 positions for the bars. Okay. Fine. Yeah, that makes sense. It'd be nice if they used a monospaced font for these. And filling the remaining 5 positions with stars. Therefore, the number of such lists is 8 choose 3. Okay, interesting. 56. That is our answer. There are 56 cardinality 5 multisets that can be made from the symbols in X. If we wanted to count the cardinality 3 multisets made from X, then the exact same reasoning would apply, but with 3 stars instead of 5. We'd be counting the length 6 lists with 3 stars and 3 bars. Yeah, 6 choose 3. Fine. In general, given a set of n elements, any cardinality k multiset made from its elements can be encoded in a star and bar list. Such a list has k stars, 1 for each element of the multiset, and n-1 separating bars. Okay, n-1. That's a good mistake I'll make later. Therefore, its length is k plus n-1. We can make such a list by selecting n-1 list positions out of k plus n-1 positions. Seen this before earlier. Very, very troubling. Positions for the bars and inserting stars in the leftover positions. Thus there are k plus n-1, choose n-1 such lists. Alternatively, we could choose k positions for the stars and fill in the remaining n-1 with bars. So there are k plus n-1 choose k such lists. Okay, so we got a choice. Equation 3.4 says these things are equal. What equation was that again? We're on page 98 now. It's that same one. Okay. I guess that makes sense. Is that, let me load that up again. Well, if you say so. I don't get it, but fact 3.7, the number of k-element multisets that can be made from the elements of an n-element set X is this formula, which I guess we just get to choose between, depending on what we like. That is kind of odd. This works because any cardinality k multiset made from the n elements of X can be encoded in a start and bar list of length k plus n minus 1, having this form with k stars and n minus 1 bars separating the n groupings of stars. Such a list can be made by selecting n minus 1 positions for the bars and filling the remaining positions with stars, and there are that many ways to do this. For example, the number of 2-element multisets that can be made from the 4-element set X, A, B, C, and D is these. Yeah, this agrees with our counting of them on page 96. Yeah, fine. Yeah. Okay. A bag contains 20 identical red marbles, 20 identical green marbles, and 20 identical blue marbles. You reach in and grab 20 marbles. There are many possible outcomes. You could have 11 reds, 4 greens, and 5 blues, or you could have 20 reds, 0 greens, and 0 blues, etc. Altogether, how many outcomes are possible? Each outcome can be thought of as a 20-element multiset made from the elements of the 3-element set. Yeah. Okay. Rather than remembering the formula in fact 3.7, it's probably best to work out a new stars and bars model as needed. This is because it is often easy to see how a particular problem can be modeled with stars and bars, and once they've been set up, the formula in fact 3.7 falls out automatically. For example, we could solve 3.19 by constructing the thing. Our next example involves constructing the number of non-negative integer solutions of the equation w plus x plus y plus z equals 20. By a non-negative integer solution to this equation, we mean an assignment of non-negative integers to the variables that makes the condition true. Okay, for example, one solution is, we can write the solution compactly as this. I suppose that makes sense. Even though it satisfies the equation, the value of x is negative, how many solutions are there altogether? The next example presents a way of solving this type of question. Okay, we can model a solution with stars and bars. For example, encode the solution such and such. Oh, right, okay. So the point is, the reason that we can't just come up with any nonsensical solution to this is because it has to have 20 stars in it. We get to choose the place the bars are going to be. So it's essentially equivalent to saying how many multisets of w, x, y, and z have cardinality 20. Okay, it's kind of cool. Yeah, yeah, yeah. Yeah, okay, fine. This problem concerns the lists. Yeah, yeah. With the property that these are ascending up to 10 inclusive. That is, each entry is an integer between 0 and 10, and the entries are ordered from smallest to largest. How many such lists are there? Okay, so in that case, we do have some extra restrictions, right? Okay, so how do they handle this? We encode such a list with 10 stars and 4 bars, where W is the number of stars to the left of the first bar, X the number of stars to the left of the second bar, Y and Z. Yep, fine. Okay. Such encodings are lists of length 14 with 10 stars and 4 bars. We make such a list by choosing 4 of the 14 slots for the bars and filling the remaining slots with stars. Another way to do this is this 1001. I don't get how they avoid the avoid them not being in ascending order. Like avoid, yeah. How do they deal with that? Yeah. So why couldn't we construct a weird? Oh wait, no, I get it. I get it. So basically, we're constructing this. We're defining it so that it's the number of stars to the left. So we get asterisk, asterisk. Just bedding this into my brain. Yeah, so this... So there's always going to be 10 in here. And indeed there are 6, 7, 8, 9, 10. Yeah, great. So this... The number of stars to the left of this is going to be 9, and it is. 6, 3, 2. Okay, interesting. So it's kind of encoded in this structure. It's kind of a neat idea. Kind of a neat framing. Very, very elegant. Ah, e to the 2 pi, 2, okay. E to the 2I pi. I was planning to raid you and everything. How are you doing? How's your stream? You've come, if you love maths and you love to see it done well, you come to the come to the precisely wrong stream. Yeah, I'm basically the opposite. I'm the opposite. I'm the opposite of e to the 2I pi, in that I do maths, but I have no idea what I'm doing. Let me do this. Let me do this cool thing. I've never done this before. Let me see if I can do it. Yeah. Yeah. Shout out. How's everyone? Makes 2I of us, maybe. How's your stream? How's your stream, e to the 2I pi? Did you have a good time? What were you doing today? Were you mathing today, or were you doing something else? Hey, each of the two iPod, are you running off, or do you want to see the do you want to see the horrendous the problem I couldn't do today? Oh, cool. Category theory again. Yeah, cool. All right, all right. So I say horrendous. This is like novice. This novice level, even to say novice is overstating it. But this will let you know where I am. So, all right. So basically, this it's this problem, which now I look at it, obviously isn't that helpful to see. But let me show you fact 3.5. Let me go to that. Okay, it doesn't go anywhere. Let's go to page 87. So 87, right. So we've got this is my chalkboard, by the way. I'm excited to show you my chalkboard. So fact 3.5 is like it's the choosing thing. It's basically like not to copy it all out, but just so that because my whiteboard doesn't support images yet, so I need to have something as a visual aid. Okay, it's this thing. You've seen this thing before. I know you have. Everyone's seen this before. It's even I've seen it before, actually. Okay, where were we? Yeah. Yeah, and then we've got page 90. Yeah, we're deriving from this. We're deriving from this the target, I guess. N plus 1 k. Yeah, so on the stream today, this is the challenge which I spent some time on and which defeated me. I don't have some of the tools, I think, as I am a novice acquiring mathematical knowledge, not a mathematician. And I managed to totally it was like a plane driving my stream into the ground as I struggled against this problem for hours. Max, I did program the whiteboard myself, though it does rely on a library by, I should credit Steve Ruiz, I think that's how you pronounce his name, of TLDraw. But yes, so it's iPad pencil driven, and yeah, it's cool. I'm building it. I'm building it as we go. So challenge 8 was the challenge. That was my challenge of the day, and I failed to complete it. I think I've been doing okay with all of the counting stuff. Anything that has like, you can calculate an answer, I'm okay at. But I don't know anything about, I don't know about proving things. This is a prerequisite to proving things, and I don't know all kinds of things. And this one ate me today. So that was the problem. What did you learn about? Did anyone learn anything new about category theory today that they want to drop into the chat? Anyone got any good new symbols, any new formulas that they've picked up? I have a hard time with abstraction. Yeah, fair enough. It's somewhere there are a set of abstract beings that are living in an abstract world, and they're like trying to work out concretions, and they're like, what? This is so concrete. I don't understand it. Whereas we have to live in the concrete world and try and work out the abstractions. Is that category theory? Maybe. Maybe. Anyway, so that was my challenge of the day. A lower level challenge, let's say. And now I'm learning about multisets. Whoa, okay. Now that is shocking to see. Okay, so this makes sense to me. Now, we got stars and bars. Stars and bars, great. Okay, we're gonna examine. Ah, hello, TTY Bitnik, great username. First time watching you live. Thanks for all the content you put out there. It's really inspiring. Thank you for saying that. I appreciate that. I'm happy to inspire. If I get people doing more cool stuff, I will be happy. Somebody came in earlier and said that these streams have, if you can believe it, inspired them to learn more mathematics. Some people watch these streams and they think, I want to do that. But that was really cool. That was really cool. I think they're going to do more cool stuff than I'm doing at the moment. Like, not to hate on myself exactly, but they were talking about like biology simulations and visualizations, like trees and ferns and stuff. Really cool stuff. So I was happy about that. Okay, we will examine one more type of multiset problem. To motivate it, consider the permutations of the letters of the word book. At first glance, there are 4 letters, sorry. So we should get 4 factorial equals 24 permutations. But this is not quite right, because 2 of the letters are identical. Yeah, we could interchange the 2 O's, but still have the same permutation. To get a grip on the problem, let's make one of the letters lowercase. Now our 24 permutations are listed below in the oval. Okay. The columns in the oval correspond to the same permutation of the letters of book. Yeah. Therefore, thus there are actually 4 factorial over 2, 12 permutations of the letters of the word book. Well, that makes sense. This is actually a problem about multisets. The letters in book form a multiset, BOOK, and we have determined that there are 12 permutations of this multiset. Max Versa says, a simple way to spot a computer scientist, ask them to draw a tree. Yeah, true. Computer scientists tend to draw them upside down, which is kind of funny, isn't it? I think Knuth says something about that, actually. He says it's just odd that they always draw them upside down. Somebody said something like that anyway. TTY says, I'm planning on reading conceptual mathematics to get introduced to category theory. I'm more in the functional programming side. That's cool. And each of the 2iPi is considering learning Haskell. I would recommend it personally as well. I learned some Haskell. I didn't learn Ewer Haskell, or is there something else that you learn Ewer? Anyway, but I did the 99 Haskell problems, and they're pretty good. They're based on some other set of problems, but they're nice way, and it's a nice language. Very very interesting set of ideas in that language, and a great way to force you to write functional programming. It's like one of the best ways to learn something is to be forced not to do anything else, and Haskell forces you pretty hard not to write anything other than functional programming. So, or if you want to write any other style of programming, you have to implement it functionally first. Okay, the columns in the oval, correspond to the same permutations of the letter. Yeah, we already did that. For another motivational example, consider the permutations of the letters of the word banana. Here there are 2 N's and 3 A's. Though some of the letters look identical, think of them as distinct physical objects so that we can permute into different orderings. It helps to subscript the letters to emphasize they are actually 6 distinct objects. Now there are 6 factorial 720 permutations of these 6 letters. It's not practical to write out all of them, but we can get a sense of the problem by making a partial listing in the box below. Yeah, it's possible to write out all of them. It's not practical, maybe. Okay, the first column lists the yeah, we get the idea. By the multiplication principle, the column has 3 factorial, 2 factorial, 12 permutations, because the 3 A's can be permuted in 3 factorial ways within their positions, and the 2 N's can be permuted in 2 factorial ways. Similarly, the second column lists the 3 factorial, 2 factorial, 12 permutations corresponding to the word a banana. Altogether, there are this many permutations of the word banana, and groupings of 12 of them correspond to particular permutations of banana. Therefore, the total number of permutations of banana is this. So let me try and work out what is being said here. So the 720. So we're doing this kind of by working out like in a single example here. And we're assuming that the single example will hold for all the other multi-sets. So it's a kind of two-step problem, two-step solution. Okay, this kind of reasoning here generalizes to the following fact. Suppose a multiset A has n elements with multiplicities p1, p2, pk, and the total number of permutations of A is n factorial over the multiplicities of all these different possible items. Okay, we have the same thing with Mississippi, we have the same thing with this. Okay, great, and then we got a whole bunch of exercises. And then if I do all those exercises, we get to do pigeonhole principle, we get to do combinatorial proof, which is our first proof of the book. Incredible. Okay, what time is it? It's almost 9. Oh my gosh, okay. I should probably, though I do want to continue, I should probably go and get some dinner. So I'm going to. All right. Thanks for hanging out today. I know this has been, at times, hard going for me anyway. But it's the software category. You know, people love tuning into the software category. There's 2 kind of software streamers. One kind where they're just like full on maximum intensity all the time, but it's the AI doing the work, and the other where the person is having a terrible time constantly for like 6 hours. We love them both. Okay, let's see what's happening. Somebody streamed with the title, now what? I suppose that's my question as well. Okay, what do we got? We got anything interesting happening? Oh, we've got a without AI channel. Oh, the dog's back. Okay. Okay, I think I've got a candidate. I've got a raid candidate. All right, I think I've selected the raid target. Target acquired. Okay, here we go. Thanks for hanging out, everyone. Have a wonderful rest of your day. I will be back on Thursday. I'll be working through more of the Book of Proof. If you tune back in a few months, I will know how to prove things, and then we'll be back with Donald Knuth, and we will learn all kinds of things from him as well. We've got 10 seconds left. Say any words you want to share. See you, TTY. And now we're out. Have a good day.